Silence is not empty. Silence is information. The universe is old, almost 14 billion years old. It is enormous beyond scale. Our galaxy alone holds hundreds of billions of stars. Many of them are older than our sun. Around those stars are planets, trillions of them across the cosmos. Statistically, life should not be rare. Intelligence should not be unique. Civilizations should have had millions, even billions of years to rise, expand, and leave marks across the stars. And yet, when we listen to the sky, we hear nothing. No signals, no ships, no visible megastructures swallowing starlight, no evidence of galactic empires, just cold radiation and distant light. In 1950, during a casual lunch conversation, physicist Enrico Fermi asked a simple question that still shakes science today: where is everybody? That question became known as the Fermi Paradox. It is not science fiction, it is not fantasy, it is a mathematical contradiction. Based on what we know about stars, planets, chemistry, and time, the universe should be crowded. Even slow-moving civilizations could colonize the Milky Way in a few million years, which is a blink compared to the age of the galaxy. Some stars are billions of years older than our sun. That means alien civilizations, if they formed, could be billions of years ahead of us, not hundreds, not thousands, billions. With that kind of head start, even basic space travel would allow them to spread across the galaxy many times over. Yet every telescope sees silence. Every radio survey returns static. Every search for artificial signals ends in zero. This is not because we are not looking. Projects like SETI have scanned the skies for decades. Powerful observatories track unusual star dimming that could hint at alien engineering. Probes study Mars, Europa, and Enceladus, searching for microbial life. Still, nothing confirms that we are not alone. The paradox grows stronger each year as we discover more exoplanets in habitable zones. We now know that Earth-like planets are common. Water appears common. Organic molecules are common. The building blocks of life are everywhere. So the question becomes sharper, more uncomfortable, more urgent. If life is easy, where is everyone? If life is hard, why are we here at all? In this video, you will learn why this silence may not be peaceful. You will learn about the Drake equation and why even conservative estimates suggest the galaxy should contain many civilizations. You will understand the concept of the Great Filter, a hidden barrier in evolution that may wipe out most intelligent species before they reach the stars. You will explore the dark forest hypothesis, an idea that suggests advanced civilizations stay quiet, not because they are absent, but because they are afraid. You will see how a simple lunch question turned into one of the most disturbing problems in science. And most importantly, you will discover the huge mistake that humanity may already be making right now. This is not just about aliens. This is about survival. It is about whether intelligence is rare, or whether intelligence always destroys itself. It is about whether silence means emptiness, or whether it means danger. Lesser-known facts make this even more intense. The Milky Way is about 13 billion years old. Earth formed only 4.5 billion years ago. That leaves a massive time gap, where other civilizations could have risen and fallen long before humans existed. Some researchers argue that self-replicating robotic probes could spread through the entire galaxy in less than 100 million years, which is still a tiny fraction of cosmic time. If even one civilization built such machines, the evidence should be everywhere by now. But it is not. That absence is not neutral. It demands explanation. Some answers are comforting, others are horrifying. And one of them suggests that the real danger is not out there in deep space, but inside the nature of intelligence itself. By the end of this video, the night sky may feel different. The stars may look less like distant lights and more like silent witnesses. Stay with me until the end, because the final idea changes everything. It challenges the belief that the universe is simply empty. It forces a deeper question about whether calling out into space is wise or reckless. If you are curious about the biggest mysteries of the cosmos, if you want to explore the science behind the silence, instead of just accepting it, this channel is for you. We break down complex ideas into clear explanations. We explore physics, space, and reality in a way that is simple but powerful. So subscribe now and join us as we search for answers in a universe that refuses to answer back. The scale of the universe is not poetic exaggeration. It is measurable. There are billions of galaxies in the observable universe. Each galaxy holds billions or even hundreds of billions of stars. Around many of those stars are planets. Over the past few decades, astronomers have confirmed that planets are not rare accidents. They are common, very common. Studies of exoplanets show that most stars likely host planetary systems. When you multiply billions of galaxies by billions of stars, and then by planets around those stars, you reach a number so large that it almost loses meaning. Trillions upon trillions of worlds exist. Many of them formed long before Earth. Our planet is about 4.5 billion years old, but the Milky Way galaxy itself is more than 13 billion years old. That means there were billions of years available for life to begin elsewhere before Earth even existed. If life started on some of those older planets, it would have had an enormous head start over us. Not thousands of years, not millions, billions. Time is the key factor here. Given enough time, even slow biological evolution can produce intelligence. Given enough additional time, intelligence can produce technology, and given still more time, technology can reach space. In 1950, during a discussion with colleagues, physicist Enrico Fermi asked a question that cut through all the numbers. If the universe should be full of advanced civilizations, where are they? It was not a dramatic speech, it was not a formal paper, it was a simple, direct question, but it exposed a deep contradiction. On one side, probability suggests that intelligent life should have appeared many times across the galaxy. On the other side, observation shows nothing. No alien spacecraft, no visible astroengineering projects, no clear artificial radio transmissions, no probes drifting through our solar system, just silence. This clash between high probability and zero evidence became known as the Fermi Paradox. It is a paradox because both sides are supported by logic. The universe is vast and old enough to produce life many times, yet our instruments detect no sign of advanced civilizations. When scientists calculate how long it would take for a technological civilization to spread across the Milky Way, the estimates are surprisingly short compared to cosmic time. Even if a civilization developed spacecraft that traveled at a tiny fraction of the speed of light, and even if it took thousands of years between each wave of expansion, the entire galaxy could be crossed in a few million years. A few million years sounds long to humans, but it is extremely short compared to the billions of years available. If even one civilization began expanding millions of years ago, its presence should be visible by now. We might see altered star systems, massive structures capturing stellar energy, or at least robotic probes exploring other stars. Yet every detailed astronomical survey shows natural processes. Stars burn normally, galaxies rotate normally. No obvious artificial signatures appear in our data. The paradox becomes sharper when we examine the numbers more closely. In 1961, astronomer Frank Drake proposed a framework to estimate how many communicative civilizations might exist in our galaxy. This framework became known as the Drake equation. It is not a single fixed number. It is a formula that multiplies several factors: the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction where life actually appears, the fraction where intelligent life evolves, the fraction that develops detectable technology, and the average lifetime of such civilizations. Each factor carries uncertainty, but many of them have become better understood over time. We now know that star formation is common. We know planets are abundant. We have found planets in habitable zones where liquid water could exist. When scientists plug even cautious estimates into the equation, the result often suggests that multiple civilizations should exist in the Milky Way right now. Not thousands in every scenario, but at least some. Even conservative assumptions rarely produce the number zero. That is important. The paradox does not require that the galaxy be overflowing with alien empires. It only requires that there should be at least one other advanced civilization somewhere. One is enough to break the silence. One civilization millions of years older than us could leave visible traces. One could send probes that slowly spread from star to star. One could construct large energy-collecting structures around its star, sometimes referred to as megastructures. Astronomers have searched for unusual patterns in starlight that might suggest such engineering. So far, every strange signal has eventually found a natural explanation. No confirmed artificial structures have been discovered. Radio telescopes have scanned the skies for decades, searching for narrow-band signals that do not occur naturally. None have been verified as alien communication. The numbers imply that someone should be out there. The sky answers with silence. This mismatch between mathematical expectation and observational reality is the core tension. The Drake equation does not prove aliens exist. It estimates probability, but when probability suggests presence and observation suggests absence, something must be wrong in our assumptions. Either one of the factors in the equation is much smaller than we think, or civilizations do not last long enough to overlap in time, or they behave in ways we do not expect. Each possibility carries implications. If the fraction of planets where life begins is extremely tiny, then we may be extraordinarily rare. If life is common but intelligence is rare, then complex brains may be unlikely outcomes of evolution. If intelligence is common but technological civilization is rare, then perhaps most species never develop radio transmitters or spacecraft. If civilizations appear but quickly destroy themselves, then the average lifetime term in the Drake equation becomes very small. In that case, civilizations would flicker on and off across cosmic time, rarely overlapping. Some people respond with comforting explanations. One common idea is that space is simply too big. The distances between stars are enormous. Even the nearest star system is more than 4 light-years away. Traveling such distances requires huge amounts of energy and time. Perhaps civilizations remain confined to their home systems because interstellar travel is too difficult. This sounds reasonable at first, but the galaxy is billions of years old. A civilization does not need to travel quickly to spread widely. It only needs patience. If a spacecraft takes 10,000 years to reach a nearby star, that may seem slow, but over millions of years the expansion continues. Each new colony could build more ships. The process becomes exponential. Given enough time, even slow expansion covers large distances. The sheer age of the Milky Way weakens the argument that space is too large to cross. Another comforting idea is that interstellar travel is physically impossible. Perhaps the laws of physics prevent practical expansion beyond a home system. Yet we already understand propulsion methods that do not violate known physics. Nuclear propulsion, fusion drives, and light sails are within theoretical possibility. None require faster-than-light travel. They only require advanced engineering and long-term commitment. Robotic probes would be even easier than crude missions. Machines do not need life support. They can travel for thousands of years. They can replicate using local materials once they arrive. A single civilization sending self-replicating probes could, in principle, explore the entire galaxy without breaking any physical laws. The absence of such probes in our solar system becomes harder to explain. A third comforting answer is that we are early. Maybe intelligent life has just begun to appear in the universe, and we are among the first. This would mean that the long age of the galaxy does not matter, because suitable conditions for life only recently stabilized. Some argue that heavy elements necessary for planets and biology took time to accumulate in sufficient quantities. There is truth in this. Early in cosmic history, there were fewer heavy elements. But by the time our sun formed 4.6 billion years ago, many stars had already lived and died, enriching the galaxy with carbon, oxygen, and iron. Earth is not among the very first possible habitable planets. Studies suggest that many Earth-like planets could be older than ours by 1 or 2 billion years. If even a small fraction of those develop life early, then intelligence elsewhere could predate humanity by immense spans of time. Another explanation is that alien civilizations are out there, but deliberately avoid contact. Perhaps they observe us silently. Perhaps they follow strict rules of non-interference. While this cannot be ruled out, it shifts the problem rather than solving it. It requires that many independent civilizations across the galaxy all choose similar behavior. It assumes coordination or shared caution on a massive scale. It also does not explain the lack of visible astroengineering. Even if aliens avoid contacting primitive worlds, they would still use energy. Advanced civilizations might harness significant fractions of their star's output. That usage could produce detectable signatures in infrared light. Astronomers have searched for such patterns. So far, the data remains consistent with natural processes. As each comforting explanation is examined, it weakens under the weight of time and scale. The Milky Way has existed long enough for countless evolutionary experiments. If intelligent life were even moderately common, at least one civilization should have emerged early enough to spread widely. Even a failed attempt at expansion could leave artifacts. Even a brief period of galactic engineering could leave detectable traces lasting millions of years. The absence of evidence grows heavier with every new survey. Our instruments become more sensitive. Our planet catalogs grow larger, yet the silence continues. The paradox forces a deeper possibility. Maybe one of the steps from simple chemistry to spacefaring civilization is extraordinarily unlikely. Life on Earth began relatively quickly after the planet cooled. That suggests that simple life might not be rare under the right conditions, but complex multicellular life took billions of years to appear. Intelligent life capable of technology took even longer. Perhaps the evolution of large brains, language, and cooperative societies is not a guaranteed path. It might require a chain of unlikely events, a stable climate, a protective magnetic field, a large moon stabilizing axial tilt, plate tectonics recycling nutrients. Each factor may narrow the window further. The more conditions required, the fewer planets qualify. Yet even if intelligence is rare, the galaxy is so vast that rarity does not automatically mean uniqueness. A 1 in a billion chance still produces many results when billions of opportunities exist. That is what makes the silence troubling. If the probability is extremely tiny, we might be alone. If the probability is modest, the galaxy should contain others. The Drake equation captures this tension mathematically. The uncertainty in each term multiplies across the equation, leading to wide ranges of possible answers. But most reasonable ranges do not eliminate all civilizations. The longer scientists search without results, the more uncomfortable the paradox becomes. Radio telescopes scan billions of frequency channels. Space telescopes measure starlight with extreme precision. Robotic missions explore our own solar system for microbial life. Mars, Europa, Titan, and Enceladus are studied for signs of biology. If even simple life were found nearby, it would suggest that life begins easily under the right conditions. That discovery would intensify the paradox. If life arises wherever it can, why does intelligence not fill the galaxy? If intelligence arises, why does technology not spread? Each failed detection sharpens the contradiction between expectation and observation. The universe appears natural and unmodified at large scales. Galaxies collide and merge according to gravity. Stars form and die according to known physics. Black holes grow in predictable ways. There is no clear fingerprint of advanced engineering reshaping cosmic structures. This does not prove absence. It only shows that if others exist, they are either rare, short-lived, hidden, or fundamentally different from what we expect. The Fermi Paradox is not based on a single assumption. It is built from astronomy, biology, physics, and probability. It is strengthened by every new exoplanet discovery. When we find Earth-sized planets in habitable zones, the expectation of life increases. When we map the age distribution of stars, we see that many are older than our sun. When we calculate galactic colonization timescales, we see they are short compared to cosmic history. All lines of reasoning point toward the same tension. The galaxy should not be silent if intelligent life is common and long-lived. So the contradiction remains suspended between numbers and observation. Billions of galaxies, trillions of planets, many older than Earth. A simple question from Enrico Fermi that still echoes across scientific conferences. A probabilistic framework from Frank Drake suggesting we should not be alone. And a sky that answers every radio transmission with static. The comforting explanations shrink under scrutiny. The scale of time erodes the argument that expansion is impossible. The abundance of planets weakens the claim that we are uniquely placed. The mathematics suggests presence. Reality presents absence, and between those two stands a gap that refuses to close. The silence may not mean that life is rare. It may mean that survival is rare. This is where the idea of the great filter enters the picture, a concept developed and expanded by economist and philosopher Robin Hanson. The great filter is not a specific event. It is a stage in the long chain from dead matter to interstellar civilization that is extremely hard to pass. Think of evolution as a sequence of steps. First, a planet must form in a stable orbit around a suitable star. Then complex chemistry must arise. Then simple life must begin. Then that life must survive disasters for billions of years. Then it must become complex. Then multicellular. Then intelligent. Then technological. Then spacefaring. Each step may look natural in hindsight because we are here. But one of these steps could be almost impossible. One of them could fail nearly every time. That step would act as a filter, stopping most life before it spreads into the galaxy. If the filter lies in our distant past, then we are incredibly lucky. Maybe the origin of life itself is unbelievably rare. Maybe the jump from simple cells to complex cells almost never happens. On Earth, simple life appeared relatively early, but complex cells took much longer. For billions of years, life remained microscopic. The transition to complex cells with internal structures may have been a unique accident. If that step is the filter, then most planets with life never move beyond bacteria. In that case, the galaxy could be full of simple organisms, but almost empty of intelligence. That would explain the silence. It would mean we already passed the hardest barrier. We would be rare but safe. Another possibility is that the filter sits between simple life and intelligent life. Complex animals may be uncommon outcomes. The development of large brains requires energy, stability, and specific evolutionary pressures. Intelligence might not be an inevitable direction of evolution. On Earth, life existed for billions of years before humans appeared. Dinosaurs ruled for a long time without building radio telescopes. If an asteroid had not struck 66 million years ago, mammals might have remained small and insignificant. Intelligence could depend on fragile chains of events. If that is the filter, then again we are fortunate. We crossed a narrow bridge that most life never reaches. But there is a darker version. The filter might not be behind us. It might be ahead. It might operate after intelligence evolves. Technological civilizations may tend to destroy themselves. Nuclear weapons, biological risks, environmental collapse, uncontrolled artificial intelligence, or internal conflict could end a civilization shortly after it develops advanced technology. If the average lifetime of a technological society is short, then civilizations would rarely overlap in time. They would rise, burn brightly for a few centuries or millennia, and then disappear. The galaxy would contain ruins scattered across vast distances, but those ruins might decay or remain too far away to detect. The Drake equation includes a term for the average lifetime of a communicative civilization. If that term is small, the total number of active civilizations at any moment becomes small as well. The sky would remain quiet, not because life is rare, but because survival is rare. This possibility carries a heavy emotional weight. If the filter is in front of us, then humanity has not yet faced the hardest test. We may be approaching it. The silence above could be a graveyard. Countless civilizations may have reached our level and then failed. The absence of signals would not be comfort. It would be warning. We would not be alone at the start. We would be alone at the finish line because others never made it this far in time. The great filter framework forces us to examine our own vulnerabilities. We know we possess technologies capable of global destruction. We know ecosystems can collapse. We know social systems can destabilize. A civilization does not need an alien invasion to end. It only needs internal failure. If this pattern repeats across the galaxy, then intelligence might almost always carry the seeds of its own extinction. The same creativity that builds radio telescopes also builds weapons. The same energy production that powers cities also changes climates. If technological growth outruns wisdom, collapse may follow. In that case, the universe would not echo with signals because signals do not last long. Yet there is another direction to consider. What if civilizations do survive, but they change in ways we do not expect? They might lose interest in expansion. They might turn inward, focusing on virtual realities or internal exploration. They might reduce energy consumption rather than increase it. They might become quiet by choice, blending into the background radiation of the cosmos. But even this idea struggles with the logic of time. Over billions of years, at least one civilization might choose expansion. At least one might build large structures. The paradox returns. Where is the evidence? A second idea offers a more strategic explanation for silence. It is known as the dark forest hypothesis, popularized in fiction by author Liu Cixin, but rooted in logical reasoning about survival. The idea compares the universe to a dark forest at night. Every civilization is like a hunter moving silently among the trees. Each one knows that others may exist. Each one knows that resources are limited and intentions are uncertain. In such an environment, revealing your position is dangerous. If you shout into the forest, you risk attracting attention from something stronger. In this view, silence is not evidence of emptiness. It is evidence of caution. The logic unfolds step by step. First, survival is the primary goal of any civilization. Second, resources in the universe, while vast, are not infinite in local regions. Third, the intentions of other civilizations cannot be known with certainty. Even if most are peaceful, a single hostile one is enough to pose a threat. Fourth, technological growth may be rapid and unpredictable. A weaker civilization today could become powerful tomorrow. In such a setting, the safest strategy may be to remain undetected. Broadcasting your location could invite destruction from an advanced society that prefers to eliminate potential threats early. Under this framework, the silence of the sky becomes deliberate. Civilizations hide their signals. They avoid building visible megastructures. They minimize detectable emissions. They may even destroy emerging civilizations that reveal themselves too loudly. The universe becomes a place of quiet tension rather than empty space. Every star could host watchers who refuse to speak first. The absence of radio chatter would not mean nobody is there. It would mean everybody is listening. This idea transforms the emotional tone of the paradox. Instead of asking why nobody is out there, the question becomes why nobody is responding. The lack of signals becomes strategic silence. The dark forest does not echo because echoes attract predators. In such a cosmos, trust is impossible at large scales. Communication across light years carries risk. Even if peaceful contact were possible, the fear of being the first to reveal your position may prevent it. Now consider humanity's behavior. For decades, we have been broadcasting radio and television signals into space. These signals weaken with distance, but they still leak beyond our solar system. We have sent deliberate messages as well. The Arecibo message transmitted information about our species and location. Space probes like Voyager carry plaques and golden records describing Earth. We have not hidden. We have announced ourselves without fully understanding the environment. If the dark forest logic is correct, such actions could be unwise. They could mark our position in a cosmic landscape where silence is the safest policy. Even if the probability of hostile civilizations is small, the consequences could be severe. A sufficiently advanced society might possess technology beyond our comprehension. The time delay of light-speed travel does not eliminate risk, it only delays it. A civilization millions of years ahead could send automated systems traveling slowly but steadily toward any detected signal source. This shifts the focus from extinction through internal failure to risk through exposure. What if the horrifying answer to the Fermi Paradox is not that civilizations destroy themselves, but that they are destroyed by others after making themselves visible? In that case, the filter would not only be self-inflicted, it would be enforced by the environment. Civilizations that broadcast loudly would be removed. Those that survive would learn to remain silent. Over time, the galaxy would fill with cautious societies that do not transmit detectable signals. The idea may seem extreme, yet it follows a certain strategic reasoning. On Earth, species compete for resources. Preemptive action sometimes occurs in nature and in human history. Fear of future threat can motivate present aggression. Scale this logic to interstellar distances and advanced technology, and the stakes increase dramatically. The absence of evidence for alien contact could be the result of successful caution by those who understand the risks. Humanity, however, is still young in cosmic terms. Our radio technology is barely over a century old. We may not fully grasp the long-term implications of broadcasting. Our early enthusiasm for contact reflects curiosity and optimism, but optimism does not guarantee safety. If the universe operates more like a dark forest than a friendly neighborhood, then our signals are not harmless greetings, they are announcements. This leads to an unsettling reflection. The great filter and the dark forest might not be separate explanations, they could be connected. The filter could eliminate civilizations that fail to manage their technologies wisely. It could also eliminate those that reveal themselves in a hostile cosmic environment. In both cases, intelligence carries danger. Survival depends not only on technological progress, but also on strategic restraint. The sky remains silent. Whether that silence is due to rarity, fragility, fear, or deliberate concealment remains unknown. But the possibility that silence is intentional changes the way we interpret every star. The absence of response does not mean absence of awareness. It may mean others are waiting, observing, choosing not to speak. And in that scenario, the most dangerous action might be the one we have already taken, sending our presence outward into a universe whose rules we do not yet understand, a universe that may reward quiet civilizations and punish the loud, leaving the night sky calm not because it is empty, but because those who endure have learned that survival favors the unseen. The real horror is not emptiness, it is awareness. Not a lonely universe with no life, but a universe filled with life that has chosen silence. A cosmos where civilizations learned, through experience or tragedy, that survival depends on staying quiet. The scariest possibility is not that we are alone. It is that everyone else discovered a rule we have not yet understood, a rule written in the silence between the stars. Think about what that means. Billions of years of cosmic history, countless planets older than Earth, civilizations that may have risen, explored, calculated the risks, and then made a decision not to broadcast, not to expand loudly, not to announce themselves. They may still exist, watching, waiting, hidden behind ordinary starlight. The universe may not look engineered because advanced societies learn to hide their engineering. It may not sound alive because those who survive do not speak first. And then there is us, a young civilization, curious, hopeful, loud. For just over 100 years, our planet has been leaking radio signals into space. We have sent messages on purpose. We have engraved our location on spacecraft. We have celebrated the idea of contact. We assume that if someone hears us, they will respond with curiosity, not caution. but that assumption is based on our limited experience. We have never lived in a galaxy where threats could arrive across light years. We have never faced a civilization millions of years ahead of us. We are making decisions without knowing the rules of the environment. If the great filter is real and lies ahead, then our challenge is survival through wisdom. If the dark forest logic is real, then our challenge is survival through silence. Either way, the stakes are high. The silence above us may be a warning, not a mystery. It may be evidence of a lesson learned long ago by others who reached this stage before us. A lesson about risk, a lesson about exposure, a lesson about what happens to those who shout into the dark without understanding who might be listening. The night sky feels calm. It feels peaceful, but peace and quiet are not the same thing. Quiet can mean caution. Quiet can mean fear. Quiet can mean that the cost of being heard is too high. If that is true, then our broadcasts are not just signals, they are declarations. And declarations in an unknown environment can carry consequences we cannot predict. This is why the Fermi Paradox matters. It is not just a scientific puzzle, it is a mirror. It forces us to ask what kind of civilization we want to become, careless or careful, loud or wise. The future of humanity may depend not only on technology but on judgment, not only on exploration but on restraint. If the universe is silent because it is dangerous, should we really be shouting into it? If this changed the way you see the night sky, make sure to like this video. Share it with someone who loves big questions about space and reality, and subscribe to the channel for more deep explorations into the mysteries of our universe. The silence is still out there, and we are just beginning to understand what it might mean.